In this video, we're going to review the solving of exact equations. This is the method 7 of solving first order equations, and you can find the other 6 methods in the description. So let's consider a function z, which is a two variable function fxy, 3x squared minus xy plus sine y. And then what we can do is we can find what they call the differential. So you learn about differential in calculus classes, normally in calc 3. So you can write a differential of a function like this. So it is da by f over da by x dx plus da by f over da by y dy. So da bars are the partial derivatives. So these two are partial derivatives, first one with respect to x and the second one with respect to y. So what will happen when we take the partial derivative? We keep the other variable fixed. So we just consider the other variable as a constant. So we're going to use the regular rules assuming the other variable is a constant. So when you do the partial derivative with respect to x, you consider y is a constant. When you do partial derivative with respect to y, you consider x is a constant. Okay. So, and then this is what we call the total derivative. So total differential. So total differential means how much change that will happen when you have change in the x and y. So these are also very important in physics or chemistry. When you do lab experiments, and you need to know how much error you get, and then this is how you can calculate actually the error. So, okay. So in our problem, so if you take the partial derivatives, so what will happen is the first one is the you can see if you take with respect to x, you get 6x minus y. That's the partial derivative with respect to x. And then if you do y, you can see it is negative x because you take with respect to y. So x are constant. So you get negative x plus sine become cosine y. So that's what happened. And then you get this equation, and you can see now we can consider a special case. So what if the fxy function is a constant function? If it's a constant function, when you take the derivative, and you can see the total differential, the change is 0. So in the special case, fxy equals c is a constant, and you can see that the change, the dz, is 0. So there are no change. So because of that, the right side of the so you can set the total differential. So we get the differential equation. You can write a differential equation now because you can set this one equal to 0. So you can write it like that. So these special terms comes because of this assumption. It's a big assumption. So without the assumption, you can write it like that. Because otherwise, you just get the total differential. But you can say the differential equal to 0 if your function fxy is a constant. So, and then we have this interesting equation. So this is a linear form of a differential equation. You can see we have dy and dx. So that means you can write this in the normal form. If you want, you can write this one as dy by dx, normal form. Otherwise, we have this one. So now the question, now if you want to go backward, so let's say you start with this and then you want to go backward. So then you can say, because of this argument, if you go backward, you can say the solution of this differential equation, this is a differential equation because there's an equal sign. So the solution of this differential equation is the original function that we start with. That's the function I start with, which is given by, you can say like this. So which is fxy, the solution is not fxy. The solution is given, the solution what we normally looking for y. So it is given by as an implicit equation. So you have to set always, you have to set this one equal to 0 because that's how we start with. So when you set this one equal to 0, this is going to give you an equation. And if you solve this equation, you get the y term. And so this is what we normally call implicit solution of the differential equation. That's the idea. And then after that we try to solve for y if it's possible, but sometimes it's very difficult. Even in this case you cannot do it because it's complicated. So we normally use a numerical solvers to do that, but otherwise this is how you can find the implicit solution of the differential equation. So let's try to talk about how actually we do it, and before that let's go through some of the definitions. So the exact equation. So we say an differential equation of this form, in this linear form, remember we always write the x terms first and then the y term, and there's a plus sign also. So if you write it like this in this form, we say it's said to be an exact equation if there is a function fxy which is equal to 0 such that the first partial derivative of that function equal the m function, and the second partial derivative, that means the partial derivative with respect to y, is the n function. So if you can, so that's the definition. So that means we say this function, this differential equation exact if there is a function that we don't know that yet. If there's a function fxy equals 0 equal to z constant such that you get those two derivatives equals to m and n. So that's the definition. Now, actually, it doesn't make any sense. I mean, you can see we know how it works if you look at the first example. Because so if you go backward, it works all nicely. But the problem is it doesn't tell you how to do it. So let's talk about a criteria. So first, actually, we have different criteria for exact equations. So what it says that let's say so we have the mxy and the nxy. That's the same two functions we talk about. Be continuous, it has to be continuous, and also have the first continuous first partial derivatives. You need the first partial derivative has to be continuous in this case. CTS for the is an abbreviation. In a open region R, then what it says that then the necessary and sufficient condition, that means works both ways, necessary and sufficient condition for mxy dx plus nxy dy equals 0 to be exact is this nice condition. So what it says that the opposite partial derivative, so that means we take the m with respect to y, we take the n, actually here the second one has to be dx, so this is dx. So you can see that the derivatives are switched. So m you take with respect to y, n you take with respect to x. So so you switch the variable. So that is the criteria. And let's see why this is the case. Let's give like a short proof. So we have this mxy dx plus nxy dy, and then we are the first partial derivative equal to m, the second partial derivative with respect equal to n. So what we do, we can start with the first side. We start with da by m over da by y, and then you can see that you can rewrite this one. So if you pull this out, and you can replace m is simply according to this condition. So you can write this one as da by f over da by x because of the condition given. And then we know that because we assume that the first partial derivatives are continuous, and then we have a advanced calculus result which says that you can actually switch the derivative, order of the derivative. So that means we can write this one as is equals to da by over da by y, da by x, and then we have da by f over da by y. So you can switch the variable. So this is not always automatic. This happened because the first partial derivatives are continuous. So from the continuity we get that, and then you can see what we have next is because we know that the da by f over da by y is n, so you can plug in it there, so that you get da by n over da by x. So that is the proof. It's a very short proof, and it because of this these two are the same. So that's the idea. Because it's the same, you can switch from one to the other. Okay, and that's the criteria. Now let's look at how to solve this equation. So how to solve the differential equation mxy dx plus nxy dy. So what we can do, first we check whether this is a exact equation, because that's the first thing to do. So you take the first partial derivative of the m term with respect to y, partial derivative of the n term with respect to x, and we say check whether they are equal. So if they are equal, then we know that's exact. So that means we're going to follow the steps. So, and if it is not exact, we're going to stop here because it's not exact, and we can use the method that we discuss here. And there are techniques to solve non-exact equations using integrating factor argument, and you can find the information in the channel, or I can probably put the link in the description so that if you need, you can find it. But here we talk about how to solve the exact equation. So that's the first step, and then the next step is so if it is exact, then by the theory we know that there is a function fxy which is equal to c such that the m is the partial derivative with respect to x, and the n is the partial derivative with respect to y. So this is coming from the definition, because that's what we mean by exact. So exact means there is such a function, but we don't know what is it, but there is such a function. Now the question is which one we're going to pick. So we picked an easy one. So we pick the easy one and partially integrate with respect to x or y depending on which one you picked, and keeping the other variable fixed. That's why we call it a partial integration. It's not a real integration, it's a partial integration. So let's do that. And then so let's say we pick the first one, da by 4 da by x over n. And then what we do, since the x, you're going to integrate with respect to partial integration with respect to x. So it's a partial integration with respect to x. So when you do that, since this is a partial integration, we don't know whether we start with a function of y, because they are versus a function of y, because the partial derivative, when you go backward, so that function is going to cancel out. So because of the uncertainty, we just add a the term which is a function of y, because we don't know, because we took the partial uh, derivative with respect to x to get this function. So when you go backward, we just leave it there. Then what we do, we take the derivative with respect to the other variable. So derivative with respect to y, which is the other variable, and then set that equal to the other, because we needed the partial derivative with respect to x, and you can see that you get da by f over da by y, which is the n function. That's the assumption because of the exact equation. So we set that equals to n. That's the next step. So we take the partial derivative first of the function that we just found, and then we set that equals to n function. But when you take the partial derivative, here you actually take the regular derivative, because you can see it is a function of a y. So you just take the regular derivative. Now what we do next, and you can see this in this equation, you can actually solve for g prime. So that's the next step. So we do the next step, we're going to solve for g prime y. So when you solve for g prime y, that means it is simply nxy minus the partial derivative. So you can write it like that. But you know, this is the theory, but when it comes to practice, it won't be this complicated. And then what happen is, so we can integrate this one with respect to y now. We integrate with respect to y and find gy. So once you find gy from this equation, now what we do, we can substitute that into equation number 2, because where you remember we had a gy term, so we're going to plug in there, and then you get the fxy. Now the question is, sometimes you shouldn't make a big mistake here. They leave that as the answer. This is not the answer, because remember, this is just fxy function, but we have to set this one equal to a constant to get the y, because we are looking for y, not fxy. Fxy is just an intermediate step. So next step is the implicit solution. The implicit solution of this equation is simply given by fxy equal to c. So you have to set this one. So this step is very important. And then what we do, if possible, we try to solve this one for a y. That's not always possible, because we get like very complicated expression for this, but if possible. Otherwise, what we do after you get to this level, we use numerical solvers to find y. So so that's the idea. So there are 9 steps when you solve a problem like that. So let's try to look at a few examples. So solve the following equation if possible. So as the first one, let's start with this. We have 3x squared minus 5y dx plus 2y minus 5x dy equals 0. So what we can do, we can go step by step argument. And so the answer, so you can see here, we have mxy equal 3x squared minus 5y and nxy equal 2y minus 5x. And then you can take the derivatives and write it like this. And you can see that if you take the partial derivative with respect to y of the first one, you get negative 5. And the other term is 0. And then if you take the partial derivative of the n term with respect to x, you again get negative 5. And the other term is 0. So, and then you can see that they are equal. So, this is an exact equation. They are equal. So, so it is exact. Okay, that's the first thing to do. We check whether it is exact. And then after that, we're going to pick the easy one. And then But here actually, because this is exact, actually we can say that then there is a fxy equals c such that, then we can say, then there is a fxy equals c such that the partial derivative of the x of that function equals to the m function, as the theory says, and partial derivative of the f function with respect to y function is the other n function. So to get, now what we do, we're gonna pick the easy one, and here it doesn't matter, you can see both are okay. So what we're gonna pick, let's pick the first one. So let's do that. So we pick the first one, w f of x equal 3x square minus 5, and then what we do, since this is a partial derivative with respect to x, you integrate with respect to x to remove that. So integrating, so integrate with respect to x. So integrate with respect to x. So when you do that, you see that you're going to get here fxy, because you remove, we integrate, and then on the other side, so it is a integral of 3x squared minus 5y. So it is not just a dx, it's a dx, because it's a partial integral. So so it's a partial. And then when you see this is a partial integral, that means y act like a constant. So you get x cubed from the first term. So y is the constant, so you get negative 5 x y. And then we also don't know that whether, normally we add a constant here. Since this is a partial integral, we add a function here. So it is a function of the other variable gy. So that's the interesting part. So if you write dx here into daba, you can't do this, because then you have to add a constant here, but it's not a constant, it's a function. So this part is coming from the partial integration. Okay, and then we can call this equation star for a future reference. And then what we do, we can differentiate this one with respect to the other variable. Since we take the x, so we differentiate with respect to y. So you get, so first term is 0, and the second term you can see that with respect to y, so you get negative 5x, and then you have gy. So when you take the derivative, partial derivative actually become a regular derivative, so it's going to be g prime y, because there are no other functions. Now what we do, we can set that, because you can see this is actually the n, dabba f of dabba y equal n, because of the exact part. So we can set this, so we can set this one equal to n function, so which is in the problem 2y minus 5x. So here we set this one, which it's not implied, we set it, and then what we do, we're going to simplify this one, because your goal is to find a g prime y. And then what happened here, you can see that the negative 5x cancelled out. Sometimes that happen, and then actually should happen, because it's g prime y. So and then what happened is, you can solve for y prime next. So when you solve for g prime y, and you can see here clearly g prime y equal 2y, you get. That's the only thing you get from this equation. You can solve for g prime, and then what you do, now you just integrate this one. So if you integrate, you get gy, and then you substitute that into the star equation here. So you can substitute that here, you integrate and then substitute there. That's how we do next. So let's do that. So integrating with respect to y, here it is clear it is y, because there are no two variables. And then so when you do that, and you can see that for you get gy equal y squared, because we had 2y, y squared. Now we can substitute that into the equation. So by star, that's the equation you're going to plug in there, and you can see that fxy equal, we had x cube already, we had negative 5xy already, and then we had the gy you replaced by y squared. So that's the one. So gy become y squared, and then you can see that is the fxy function. Remember, this is not the solution, this is just the fxy function. Now what we want to do, we can set this one equal to a constant. So the implicit solution is given by, what do, you set this function equals to a constant. So that means you can write given by x cube. So you can say f x y, which is x cube minus 5xy plus y squared equal constant. So that's the important part. And you can see this is an equation here. Or if you want to remove that, you can just say given by simply, you can just write x cube minus 5xy plus y squared equal constant. You can just write it like that. But remember that you have to set it equal to 0. Now what we do, if possible, we're going to solve this one for y. So we have this step, so solve for y if possible. And in this particular situation, actually you can solve. You can use the quadratic formula to solve this one. So let's do that. So we can use the quadratic formula to find y. So we start with the equation and then we can rearrange them. So we can write this one as y squared minus 5xy, and then we put x cube here and bring the c term there. And when you do that, you can see this is in the a squared plus bx plus c form. And here you can see that you can actually have an extra 1 here if you want. So you can see a equals to 1, and then a b equals to negative 5x, and then this is the c term. So we can plug in this in the quadratic formula, and then we get this, and then you can simplify. So you get this one as the y as a function of x, and then depending on the c value, you can get different answers for this one, real, repeated, and complex. Okay, so that means there are certain situations where you can actually solve for y directly. Okay, so let's look at the next one. So as the next one, we have ex plus y dx plus 2 plus x plus y ey dy equals 0, along with y0 equal 1. So in this problem, you can see that the first one, so which is the m function, and then this is the n function, and then let's take the derivative and check whether this is exact. So we have m and n. So now we take the derivative. So you see that da by m over da by y equal 1 and also equals to da by n over da by x. So this is exact. So then we pick the easy one, and you can see clearly the easy one is the so this is exact. So that means there is a function f such that m equal da by f over da by x, and then n equal da by f over da by y. So we pick the easy one, the first one, because that's easy to work with. So then there is fxy such that e da by f over da by x equal the first function, which is ex plus y. So we're going to continue with this one because that's easy to work with. So when you integrate this, so we get f xy equal, so this is ex, and then when you integrate with respect to x, you get xy, and then again plus a function of function of y, so gy. So let's call this equation number 1. And then what we do, we take the derivative of the other variable. So in this case, differentiate with respect to y. So you get da by f over da by y. First one is ex function, so you get 0. From the second one with respect to y, so you get the x because it acts as a constant. And then you get g prime y. Now what we do, we can say this one equals to n. So in our case, n equals to 2 plus x plus y ey. So we set here because this is the n function. Now what we do, and you can see x and x get cancelled out. So you get g prime y equals to 2 plus y ey. Now what we do, we can integrate this one to get y. So we integrate term by term. So the first term going to give you 2y. The second one is the integral of y ey. For that we had used the integration by parts. But what we normally do, we use a shortcut for in these situations. So let's do the shortcut and get the answer. So we use a shortcut, or what we call the di here, and d we're going to pick as the y term, I we're going to pick as the ey term. So d term and the I term. Okay, so we take the derivative of the first term with respect to y now. Integral, you get ey. Derivative, so you get 0. Integral, you get ey, because we are taking the integral with respect to y here. Now what we do next, we're going to multiply across the diagonal. That's what happened in the DI method. And if you are not familiar with the DI method, you can find the link in the description with a few examples there. Okay, so now we can write the solution. So you can see it is 2y, the first one, and then the first product, which is ey, and then the second product. So you find the product along the diagonal. So we can start with the first diagonal and then the second diagonal. That's how we do. So you get the next one is minus ey. We don't add a c here. Okay, that's the gy term. Now what we do, we're going to plug in that into the equation 1. So we're going to get this. So you can substitute here. So that's the one we already have. And then we had the gy term. That's a gy term. Okay, so now we can set this on equal to constant and find the implicit solution. The implicit solution is ex plus xy plus 2y plus yey minus ey equals to a constant. So this step is very important. Okay, and then, because this is an equation, and then if possible we can solve this one, but this is not easy to solve. So what we do, we can use the initial condition now. So let's use the initial condition. So using the initial condition, in this case y0 equals 1, so we can plug in that. So you get 1 because e0 equal 1, and then you get a 0 term, and you get a 2 from the next one, and then you have ey, e1 in this case, so e1, and then minus e. This equals to c. So this says that c equal 3 because e get cancelled out. So that means now we can write the solution. Just set this on equal to other constant. So the solution is, so the implicit solution is, so ex plus xy plus 2y plus yey minus ey equal to 3, and this is the implicit solution of the equation. And you can so y is a solution, but this is implicit equation, implicit solution, what we normally call, and this is not possible to solve this one easily. So yeah, so let's look at the next one. Suppose we have 2x y cube plus sin x dx plus 3x squared y squared dy equals 0. So we again we're going to pick the m and n. So that's the m and the n. So we're going to check the condition. You get 6x y squared, dabba m dabba y equals 6x y squared, and you can see that this clearly equals to dabba n over dabba x. So that means this is exact. So we're going to pick the easy one. And in this one, actually, it's clear that the second one is easy, not the first one. So we're going to pick that one. So let's do that. So then there is fxy equal constant such that dabba f over dabba y here, which is the n function. So we put the n one in this case, which is equals to the equal to 3x squared y squared. Okay, and then what you do here is a derivative with respect to y, so we integrate with respect to y now. So again, why we pick this one? Because you can say that's easy to integrate. It's easy to work with, less terms. Okay, so let's integrate. So you get, so the integral of 3x squared y squared dabba y here, because integrate with respect to the partial derivative y. And when you do that, you can see you're going to get, you're going to keep x as a constant. So you get y3 now, and divide by 3, so you get x squared y cube, and then a function of x because of partial integral, because of partial integration. Okay, so now we take the derivative of this one with the other variable. Since we picked the y variable here, now we take the derivative with respect to x variable. So you take the different derivative with respect to x, you get da bar f over da bar x now, so which is equal to 2 comes in front, so you get 2x y cube plus h prime x, that's very clear. And then so this is the x derivative, that means this is equal to m, so you can say this one equals to m term. So let's do that. So which is equals to 2x y cube plus sine x. That's what we had in the problem. So we set, and then what you can see that this term get cancelled out, so you only get x terms. So that should happen always, whether you can do this step. And then you're gonna solve for h prime x and then solve for hx. So this says that h prime x equals to sine x, and integrating you get hx equals sine means negative cosine x. We are not going to add the c. Now we can plug in that into the formula. So we can plug in that here. So we can plug in that here. So so the implicit solution is given by fxy equals c. So in this case, what happened is x squared minus y3 minus cosine x equals to c. In this case, actually, you can solve for y. This is not difficult. So solving for y, we get y equal cube root of c plus cosine x over x squared. So that is like a explicit solution. So sometimes you can do that, and then if you know the initial condition, you can find c. So let's look at one last problem before we discuss the shortcut method. There's a shortcut method that you can get the answer very quickly for exact equations. So let's look at the last one. Say we have this one, and clearly so that's the m and n. So we check the condition. So da bar m over da bar y equal 3x squared minus sine y, and da bar n over da bar x equal 2x, and you can clearly see that they are not equal. That means it is not exact. So there are certain ways to solve these kind of equations using integrating factor argument, but we don't discuss it here. So if you want to know more about that, you can find them in the link in the description, how to solve non-exact equation, what we call like almost exact. Okay, so let's look at the shortcut method now. Let's discuss the shortcut method to solve the exact equation. And you know that when you want to solve the exact equation, it needs like 8 steps. So here we can do it quickly, we using like only 3 steps. So let's see how it works. So the idea is this: we start with the equation. First, as in the other method, we first need to check whether it's exact. So let's do that. So if the partial derivative with respect to y of m equal partial derivative with respect to x of n equal, they are equal, then we know that is exact. So that means there is a function fxy such that it gives the partial derivatives. The x partial derivative with this, gives the m function, the x1 gives the m function, and the y derivative gives the n function. So that's by the definition. That's what we call exact equation. And then what we do now, we integrate them term by separately. You integrate the first one by x, the second one by y. So integrate separately. From the first one we get this. So you will get some expression of x and y, and here you integrate with respect to partial integrate with respect to x, keeping y fixed. Now do the same thing with the other one. So you integrate partially with respect to y, so you get another expression. So now the answer is this. So then if xy equal, first we take the common term. So we look at the both expressions. So we look at both expressions and write common terms once. You write the common terms once and then you write uncommon terms once. So you write the common terms once and the uncommon terms once, and this is going to give the fxy function. And then what we do, we set this one equal to a constant, and that's going to give you the implicit solution of y. So that's the idea. So let's look at a few examples and see how quickly we can get the answer. And also you can find the link in the description if you need more examples like this. So you can find this problem in the ZIL differential equation book, and let's see how we can use a shortcut to get the answer quickly, just for comparison purposes. So as before, we identify the m function and the n function, and then we can check the condition. So you can see the two partial derivatives are equals to 2x, so it is exact. So that means there is a function fxy such that the partial derivative with respect to x equal m function 2xy, and partial with respect to y equal the n function x squared minus 1. Now what we do, we integrate them separately, and we get x squared times y plus some terms. So we can just write 3 dots, and then if you from the second one, that is with respect to y, so you get x squared y minus y and some terms. So now we pick the common one and the uncommon one, and you can clearly see that that's the common term, so we write once, and then this is the uncommon term, we write that one also once. So then fxy is, so we write the common term once, so it is x squared y, and then minus the uncommon term, which is minus y. So we just set this one equal to a constant. So that is the implicit solution of y. And then actually you can see that in this case you can solve for y. So y equal, you get, if you divide, you can get c over x squared minus 1. So that is the complete solution for this problem. And you can see this solution is defined when x not equal to plus or minus 1. So you can see that this is how you can solve the exact equation very quickly using a shortcut method. So let's look at two more examples. Next, we look at this problem from the same book for comparison purposes. And you can see again, we can pick this one as m and the other function as n. And then we check the condition using the chain rule. So first, there's the first term is 2e 2y. The second one you have to use the product rule. So if you use the product rule, we take the derivative of the first term, so you get y, and then you get the cosine xy, and then you get minus y times, and you can see it's a cosine, so cosine becomes negative sign, so it becomes plus sine xy, and also you need to multiply by the derivative of the inside function. But here remember x is a constant, so you're gonna so you get the x term comes out. Okay, so that's the derivative, and then you can see that if you take the derivative of the n term with respect to x, and you see that you get the same thing. So they are equal, so that means exact. So then there's a function fxy such that da by f over da by x equal the m function, da by f over da by n, da by f over da by y, da by f over da by y equal the n function. Now integrating separately, first with x, next with y, we get these two. So the first term is clear, is x e to y. But what about the second one? Second one, you have cosine xy, that means you have to start with sine term. Since this is a partial integration, you can see the y comes out as a function. So that means it has to be sine xy. If you take the partial derivative, you get the function we have here. And then plus some terms, we just put it like that. And then similarly from the other one, so we get the first two terms as before, and also we have a 2y, that means you get y squared extra term, so plus 3 dots. Okay, now we write the common and uncommon terms, and you can see these uh, two common and these also common, so we write them once, and then we write the uncommon term, which is y squared, once. Finally, we set this one equal to c. This is going to give you the implicit solution for y. Okay, so this is how we can solve a exact equation using a shortcut method, and just compare. If you want to do this using the regular technique, it's really long because of the expressions we have here. But this method, like, not that bad, and you can get the answer much quickly. So let's do one last problem from the same book. So now we have a equation in a different form. It's a normal form now. So dy by dx equal xy squared minus cosine x sin x divided by y minus x squared. So what we can do first is we have to write them in the linear form. So let's do that by cross multiplying. And then we can bring all the terms to one side, having the dx term first. That's going to squeeze the sign of these ones. And next we check the condition. You see that two partial derivatives are equal, so it is exact. Then there is a function f such that. So now we integrate them separately to get this. You get this from the first equation, and you can see that here we have the cosine sign. When you have the cosine sign product, you can consider one as the derivative of the other one. So the easy way to do that is assume cosine is the derivative of sine. So because of that, you can write this one as 1/2 sine squared, because if you take the derivative, you get 1/2 2 sine x cosine x, which simplifies to sine cosine. So that's the easy way to write it. So similarly, from the second one, integrating with respect to y, we get this one. This you can distribute and write it like this, and then you can clearly see that so this is the common term that you have, and the other two are the uncommon terms. So this is uncommon and this is also uncommon. So we can write the final answer like this now. Now to find the solution of the differential equation, we can set this one is equal to c. So let's call it c1, and then we're going to multiply by 2 just to simplify. So then you're going to get this one as the final answer. And here you can see the c equal negative 2c1 because just you can write it like that just to make it simple. Okay, and then you can solve for y if you want, and but this one is the implicit solution for the equation. So now you can try these practice problems using any methods you like, and compare the two. So let's do that. Solve the following differential equation if possible. Here we try to focus on the exact equation technique. So see whether you can use the exact equation method, either long method or the shortcut method, and also check whether this is exact first, and you have to bring it to the right form first, and then you need to check the condition, and then use one of the methods to solve it. And if you have any comments, then you can put them in the comment below. Thank you so much for watching.